How's your wife? Is she still sick?
My wife is still sick, but I'm still kind of more sick than she is. It's kind of sad. All right, so I got a question, real fast. Kalena and Deja, do you understand this a little bit better now? Can I erase this? Okay, good. I appreciate that.
Happy Chinese New Year, everyone.
Oh yeah, Konki Fatoi. Um,
Happy Chinese New Year.
I said Gong Hee Fa Choi, but like in a American accent, right? Like how do you say it?
恭喜发财.
Oh, whoa, go! I had it wrong my whole life.
That's my
What
religion.
is that?
Yeah, that one, see, that's just matter. But then there's another one that's in Cantonese different. So.
Oh, really?
At the same time, I couldn't hear the Chinese of this.
I always thought it was Gong Hee Fat Choi, yo.
Yeah, I mean, that's how you spell it. But
Gong Hee Fat Choi. All right. Anyway,
because that's a Cantonese spell.
yes, I know. It's because I'm so darn Americanized, even though I'm half Chinese. I'm actually half Cantonese, but anyway. Yeah, I know it's sad. All right, I introduced to you guys this idea, and here's the thing that I think really kind of came into confusion. There's a difference between what we call the electric potential energy, which is we call it as U, which we define U as um, Q naught E times D. Actually, it's negative Q naught E D. And then there's this other thing called electric potential, which is defined as V, which is actually U divided by Q naught, which is just ED. Negative ED. And that like those two equations are actually different. They're obviously related to each other, right? But I mean, they're different. I guess the difference being what's the difference between kilograms and like all right, so this wouldn't necessarily be the greatest analogy, but this would actually kind of work, I think. What's the difference between kilograms and um, what is the difference between oh here this would be even better. When I ask people what force is being is pushing down on this object right here on this book or something like that, everyone tells me gravity. They tell me gravity, right? They say gravity. Gravity is the force of that. And then I don't even know if you remember, but Tiger, but in the beginning of class, I burned you a lot for. I didn't burn you specifically, but I burned a lot of people for saying, no, it's not gravity. Gravity is not a force. Gravity is an acceleration, right? The weight is the force that we're talking about, which is if force equals ma. And by the way, please, Deja and Kalina, don't look at this and be like, oh my gosh, he's introducing more equations to us. I'm just using this as kind of an example, but if the force is equal to ma, but the weight is defined as mass times gravity. So is gravity related to the weight? Yes. But is it the same thing? No. There's a small little factor. Or even, here's an even better question is, what's the difference between mass and weight? Because a lot of people use those interchangeably. They say, oh, the mass is this, and then they're like, well, it weighs this much, and they're like, no, it's not, that's not the weight, that's not the mass. Mass, the mass is something inherent to the actual thing. The weight is that mass times gravity. Well, are they related? They're totally related. They're totally related by this G. But are they the same thing? No. You can obviously see that by just looking at the equation. We cool? So, so kind of the idea. All right, fine. I'll turn on the face cam so you guys can see my face. So the idea that we had here is I introduced to you guys the electric potential energy, and then I also introduced to you guys the electric potential, and I kind of sucked at making a distinguishing between the two of them, and I think that that's kind of what added a lot of confusion today, or not today, but just like with this stuff. Why am I? Why is this not working? No, but the cam isn't working all the time. I want to try to set it up so I can get it to out to a specific position. There we go. All right, okay, there we go. So it's on me now. All right. Anyway, I think I'm going to go through the rest of this chapter, and I think that we have a better picture, a clearer understanding of what's going on. So we should be able to handle this stuff pretty nicely. Anyway, let's do. We talked about the conservation of energy, and how was that for you guys? Well, no, I mean, the conservation of energy was actually not that bad at all. All right, so here, it's the equations that freak you out? All right, fine, I'll tell you what. Let's do this problem together. Say that we have in fact, write this down if you guys have a pencil and paper. Say that you have a battery, and there's a capacitor. And I didn't explain to you guys what a capacitor is. A capacitor is really just two plates of metal put next to each other, and they're separated by a certain distance. Okay, I usually have to tell you what that distance is if you want to calculate the electric field on it. But let's say that this this capacitor is attached to a battery. There's a positive side to this battery, and there's a negative side to this battery, and so the difference in potential is here's VA, here's VB. VA minus VB is equal to 12 volts. Okay. Does that tell you which one's bigger? Is VA bigger or VB is bigger?
VA.
VA is bigger because VA minus VB is still a positive number, right? So that must mean that VA has to be a bigger number than VB. Because if you were the other way around, then you would get a negative. You could have a negative voltage, and all you do is you take your battery and put it backwards, right? So, but if this has a positive voltage across it, then you know that the potential is kind of going down, and a positive charge will want to flow in the direction of the lower potential. I mean, if you kind of think about it, like if you have something on a hill, right, and you put a ball on the hill, it has a high potential over here, it has a low potential over here. Where will the ball want to go? To the lower potential. Right, it will roll down the hill. That's kind of the same exact thing. Actually, that's exactly the same exact thing. So let's talk about this. So my question to you is, say that it starts at 0, so velocity is equal to 0, and say that velocity at B is equal to, I don't know, they said 3.4 meters per second. This is actually going to be kind of good. I think this is going to be a good problem. Right. Then what you do is you ask yourself, okay, fine, what is the mass? What is the mass? That's my question. Of this object. So, what you do is this. You kind of account for all of the energy to begin with and set that equal to all of the energy at the end. Because remember, I told you, the law of conservation of energy basically states that everything you add up in the beginning has to equal out everything you add up in the end. So, what kind of energy does it have here? Does it have kinetic energy? Why not? Why does it not have kinetic energy? Because I told you it started from rest, right? Over here, does it have electric potential energy?
Well, if it's at rest, then we have to work, right?
Yes. Well, I mean, even if it weren't at rest, it has electric potential energy because there's a electric field pushing this thing down. It's going to want to move. Even if I was holding it at rest, it's going to want to move. Okay? So we have these, it has an electric potential energy here. Over here at the bottom doesn't have kinetic energy. Yes, it's moving. It's moving exactly at 3.4 meters per second. Does it have electric potential energy? It could, but it has less. It has less than from before. All right. So here's what I'm saying is, what I want you to do is I'm going to add up all of the energies in the beginning, and I'm going to add up all of the energies in the end. And that's the symbols I would use. That the funny E looking things means add up everything, and then The U means all the energies. So, yeah, I guess I could do it that way. Maybe I should put. I don't want to put E because that looks like the sigma, and it also like E is something totally different. So anyway, I'll just write it like this: kinetic energy initial plus electric potential energy initial is equal to kinetic energy final plus electric potential energy final. Are we cool? Right. That's what I'm talking about. Or in this case, I'm just talking about Q times V. Q times the voltage. So this right here is 1/2 mv squared, but we talked about how what V initial was, that's 0. So 0 squared is 0 times 1/2 m, still 0. M is the mass. And that's what I'm trying to figure out. That's what I'm trying to solve for. What is the mass? This right here is Q times V, and that's the voltage at A. We cool? This right here is 1/2 mv squared, and that's the V final squared, which is 3.4. I know what that is. And then this right here is Q times VB. We cool with that? Now all I want to do is I want to solve for, oops, you're right. I want to solve for M, not V. I want to solve for M. So in order to do that, I would simply take this over to the other side. So I would have Q times VA minus Q times VB, or can I just write it like this? Equals 1/2 mv final squared. Deja, are you good with that? Because I don't hear your voice. I'm not picking on you because I don't think you understand. I just don't hear you.
Yeah, sorry.
Alright, it's alright.
I don't know.
Alright, cool. I know what VA minus VB is. I told you what that is. That's 12 volts. So all I got to do is solve for M. Okay, fine. How do I get rid of the 1/2? Multiplied by what? Multiplied by 2, exactly. That gets rid of the 1/2. How do I get rid of the V final squared? No, I'm not. If I square root it, what that would imply is I'm trying to solve for V. I want to get rid of the V final squared. I don't need to get rid of that square. So yeah, just divide by the whole thing. There we go. So that's my M. And then you solve for M. Boom, that's it. Oh, what happened here? I think the computer lags a little bit. Alright. So that's it. That's it. You just plug in 2 times the charge, which is 6.24 times 10 to the negative 6 coulombs. And actually, I think that they gave me this in the previous problem, and I just forgot to write it down. The VA minus VB, that's 12 volts. The V final squared is 3.4 squared. And so your mass is, yes, the Q is whatever the charge is on that thing that's being pushed. We cool? Alright. Then the mass. What is that?
What's the name of this equation?
Which one? This one right here?
Yeah.
It doesn't have a name. In fact, I wouldn't encourage you to memorize this because this equation is specific to the problem we're solving. The one you really want is really just this idea right here. And it's not really an equation. It's kind of just a concept. It's called the law of conservation of energy. It's basically saying all the energy in the beginning is equal to all the energy in the end. Does that make sense? And I taught this to you before, Tiger. I taught this to you when we didn't have a U, we had potential energies to deal with, and we had spring energies to deal with. But it's the same thing. It's the same thing. I said, okay, you want to account for all the kinetic energy and all the potential energy from gravity, and we want to talk about all the spring energy and add that up and add that and make that equal to all of the energies in the end. I'm doing the same exact thing with you but this time I'm introducing it to you a little bit slower because we've had other people who haven't had this concept yet, and all I'm doing is I'm replacing the potential energy with an actual like electric potential energy, which is something we didn't cover back when we were talking about classical physics. But you remember this, right?
Yeah.
Yeah. All this is the same thing that your fourth grade taught you, where you says all the stuff you have in the beginning should equal all the stuff you have in the end. You know what I mean?
Yeah.
I can't like create or destroy anything. All this energy has to remain the same. Yeah, you do it in chemistry, and you do it in that. So anyway, here's what you get. You end up getting 1.3 times 10 to the negative 5 kilograms.
Part of it is that you go so fast at it.
Is that? Oh, you mean I do it without a calculator?
Yeah, you're the one who work with the other ones because it also works.
All right, fine. I'll do it with a calculator. 2 times 6.24 times 12 divided by 3.4 squared. So let's pull this thing down so you guys can see my thing. I want to go to 2 times 6.24 squared times 12 divided by 3.4 squared. Actually, this 6.24 is not squared. And my answer is going to be a really big number. 1.29 or 1.3 or not 1.3 but 13. So my answer is 13. Oops, I didn't want to press close. Whatever. My answer is 13. But I didn't throw in that thing right there. Times 10 to the negative 6. So that's actually 1.3 times 10 to the negative 5. Yes, I did all those calculations. I didn't do it in my head. I'm just copying it straight out of the book because I'm looking at the example problem there. But I figured you guys don't need to know how to plug in numbers into your calculators. You guys should be able to do that. But you're right. I should give you time to do that. So yeah. Yeah, you know what? And here's the problem is it's hard for me because I feel like I've hammered this concept into my regular physics students, whereas with you guys, like you've been with me, but you haven't been with me in physics, and so I might be going a little bit faster. And if I'm going too fast, slow me down. I don't mind. Stop me. Whatever. Okay. All right. Here, I got a question for you. Ready? Say that I have an electron. And an electron has a charge of Q equals negative 1.6 times 10 to the 19, or negative 19 coulombs. It's a small negative charge. Cool? And I have some potential V, positive V. Got it? So what is that electron going to do? It's going to fly really fast that way. We cool? All right. Now let's say I have a proton. And the charge on the proton is Q is equal to positive 1.6 times 10 to the negative 19 coulombs. So a proton has the exact opposite charge of an electron. But say this time I'm going to put it in a negative potential energy, or potential field, and it's going to fly this way. It's going to be attracted to the lower side. Cool? Which one will go faster? They both have, well, I would say they both have the same charge, but they don't both have the same charge. They both have opposite charges of each other. And I'm putting it in the same size potential field, just opposite sides of each other. Which one's going to go faster? Why? Why is the electron going to go faster? Yeah, there we go. You got to think about that. A lot of people would say, "Oh, it's the same. It's the same speed because they have the same charge, and they're putting the same force really, or potential field. Wouldn't they go the same speed? And then you have to keep in mind that, like, yes, I guess that's true, but the electric, the potential energy is going to be, the electron is easier to move than the proton because the proton's way more massive. It's like 1,000 times, a couple thousand times. I think. Let's see. The mass of an electron is times 10 to the negative 26, whereas the mass of a proton, I think, is times 10 to the negative 24, so it's about 100 times. Yeah. Anyway, it's bigger. Protons are way bigger than electrons, and we covered that. We talked about that. All right, are we cool with that? You guys understand this? Like that race would win?
Yeah.
Right. Cool. So here's what we're gonna talk about. We're gonna talk about, well, what is the potential energy of a point charge? And what do I mean by point charge? We're just talking about like a proton in the middle of the room. You know what I mean? So what is the potential energy of that? All right. Well, let's see. If I have another test charge over here that I'll call Q naught, and I'll call this one Q. What's the force in between them? Yeah, they're both positive. You guys remember that? What's the force in between these two guys? Yeah. What force are they pushing off each other with? If I show you the equation, you're like, oh, I remember that. Force is equal to K, Q, not Q over R squared. Let's call this point A, so this will be RA squared. Sound good? All right. What is the electric potential energy between this? Well, electric potential energy is the work, right? Work is equal to force times distance. So really, the electric potential energy at A is just this times the distance, which is RA. So it's really just K, Q naught, Q over RA. No square. Does that make sense? Did I lose you? Right, but that's talking about the electric field. But it's also different. This is the electric potential energy. Which is the same. You're right. E, D is the same as that. Because E is... I have an equation back there that says E is equal to, what is it? It's Q... I forgot what that equation is. I gotta go look it up. But I mean, it's the same thing. That's saying the same thing. Essentially, the U is equal to force times distance. The distance I'm using for this is RA. So I just multiply this by RA, and you get this cancels out with that, and you get 1 over RA. We cool? You sure? We're good? What's going on, Austin? I'm explaining some heavy stuff. All right.
Are you archiving this?
Yeah, I'm archiving this. Let's talk about. Let's move our test charge to point B. If we move our test charge to point B, what is my new electric potential energy? It's very easy. What is it? And then instead of talking about point A, I'm talking about point B. What's my new potential energy? Electric potential energy. I'll write it down for you. KQ naught Q over RB. The potential energy at A was over RA. The potential energy at B was over RB. Does that make sense to you? All right.
Yeah.
So what's the difference in between these? KQ naught times Q? This is really just the force.
Okay.
What's the force in between? Because I've got the charge on one, I've got the charge on the other, and I've got divided by the distance squared. But then I just take that distance squared, and instead of using the distance squared, I'm just going to use just the distance and not have the distance squared. Because I'm talking about the difference between this is the force itself, and here's the energy. Have you guys ever noticed that? Does that make sense to you?
Yeah.
I can justify it to you physics students. You're going to have to take it at face value for those of you who haven't had physics. Essentially, think about this. What's the equation for potential energy when we're talking about gravity. We're talking about mgh, right? What's the equation? This is the potential energy. This is old school. And by the way, if you haven't had physics, don't worry about what I'm talking about now, right now. What's the equation for the weight?
B.
What's that? It's just mg, right? This is the force. This is the energy. What's the difference between those two equations? I don't know if you never noticed it. It's just the h. It's just a distance. So all I'm doing is, in order to turn this force into a energy, I just multiply by a distance. And that distance that I'm standing away is RA. So I change my force into energy, and then there we go. Bada bing, bada boom. What do you want from me? Yeah, exactly. Are we cool with this?
Yeah.
All right. Now, let's do this. K. Let's figure out what the difference between them is. We've always been talking about what's the difference between this electric potential energy and this electric potential energy. I've got K Q naught Q over RA minus K Q naught Q over RB. I can pull out a K and a Q naught and a Q, really. But let me just pull out the Q naught for now. Well, let me do this. How do I make a UA into a VA? I'm changing from electric potential energy to just electric potential. U is equal to Q times V, or V equals U times, yeah, exactly, U equals Q times V. U equals Q times V, or better yet, V equals U over Q. If I know what U is, then I can figure out what V is. So I just got to divide by Q naught. I just got to divide by my test charge. Sound good? So I'm going to take this equation, and in order to get VA minus VB, I'm going to take this equation right here, this is divided by Q naught, and all that does is get rid of these Q naughts. So KQ over RA minus KQ over RB. Are we cool with this? Am I blowing your mind?
Yeah.
Or this isn't that bad? I'm serious. I'm serious. Once I explain this to you, you guys are like, oh, I kind of get this. So what do we just find? All right. We found what is the potential difference between if you take a test charge and you have it here versus if you take a test charge and you have it here. That's all we did. And where did that potential difference come from? Well, it came from a test charge that was originally right here. This test charge will have these field lines like this. And then if I take a little test charge and I put it here, actually this isn't a test charge, this is a regular charge. If I put a test charge right here and a test charge right here, I can figure out the potential difference between point B and part A. That's all I did.
Okay.
Cool? But what I want to do is I want to figure out, well, what is the potential difference if I just have one point? I don't want a difference between point B and point A. I just want point A. I just want to know what is the electric potential at one point in this thing. So what should I do with that second point?
To figure out.
Yeah. If I want to figure out what, if I want my equation to be, what is the electric potential at a single point? What can I do to point B? Why don't I do this? Why don't I do this? How's about this? Why don't I take B and I make it really, really big? If it's really, really big, what kind of electric potential do you think it's going to feel from this charge over here? If the distance is really far away, if I take this test charge and move it to like Antarctica, it'd be small. In fact, here's a new concept for you, and this is kind of what we do in calculus. If I make RB so big, the distance so big, that it's like almost infinity, what would this number effectively be? It would be 0. And we can just kill it. So now we have the voltage at A is just KQ over R.
Why is the electric potential energy equal to the voltage? That's like.
Yeah, why is there a difference between electric potential energy and
Why is this equation the same as this?
why is which equation?
Like,
Oh, no. This equation is not the same as this one. They're different. The difference is I had to divide this one by Q naught. Because voltage is equal to the electric potential energy divided by Q naught.
oh,
Yeah, I just divided by Q naught. That's why I got it.
So that's your second step, basically.
Yeah,
Okay.
I suppose that I should have written that one down, or maybe, I don't know, I thought I was being
Well, it's just because if it's V right there, and you just bought it by Q naught.
Yeah.
Two.
Yeah. So, the potential energy of the electric potential of a point charge is just kq over r, and that's it. It's k times whatever your charge is divided by r. So, if you tell me, okay, you have a point charge in the middle of nowhere, okay? What is the, in fact, this is an example problem, let's see. So you have a point charge in the middle of nowhere, and the charge on this, the Q on this, is equal to 6.8 times 10 to the 7 coulombs. Or, I'm sorry, negative 7 coulombs. 10 to the 7 coulombs would be really big, I'm sorry. So it's negative 7 coulombs. What is the electric potential if you are standing a distance 2.6 meters away? Well, all you do is you just say, plug it in. I don't know what's hard about this. You just plug in this over here. You know what K is and you know what R is. And that's the electric potential at a point this far away. Does that make sense?
Electric potential. Not electric potential energy, electric potential.
It's electric potential
In volts.
in volts.
Does it ever matter what the is 8.9 or just straight?
No, that's just a matter of being an approximation. What Austin is asking is, if I use 8.99 times 10 to the 9 as opposed to 9 times 10 to the 9,
9.81.
yeah, it's kind of like using pi equals 3.14 versus pi equals 3. You know, depends on how accurate you want it to
But
be.
you're multiplying it to the 9 that you're missing out about. Multiplying to the 9 you're missing
No, he's not saying change the exponent. He's change the number in front.
But if you change the number in front, you change it to your result when you multiply
No,
it.
no.
Because if the expression's the same, I always listen.
It makes it by almost maybe 10 million.
Nope.
You're going to be off.
No, but I mean, see, that's the thing is, in physics, what we do is we're really only concerned about like the exponent. We don't even really care about the number.
Yeah.
Because I mean, the number can change a little bit, but if you mess up the exponent,
Then it's completely off.
then you're totally off.
So, but then we're comparing like 80 million, 990 or something.
Right. You're off by a whole zero, and that's a big deal.
8.99 times 9 is 5. It's like what?
Right.
8.9 billion.
Well, okay. So anyway, if you plug this all into the equation, you're going to get 2,350 volts.
That's quite high.
That's a big voltage.
It's quite high.
Yeah. But times 10 to the negative 7 is kind of a big charge. Even though it seems like it's a small charge. You cool?
So if you were to say add maybe that negative instead of the x negative instead of putting that not negative, you kept it as a positive times the sign, that voltage would be much smaller.
Times 10 to the, oh, yeah. Oh, no.
Maybe because of the
It'd be, you're talking about, oh, no, you're talking about if I have a positive 7 over here instead of a negative 7?
You would add it.
No, that would change the Q, and that's in the numerator. That thing would be 2350 times 10 to the 7 volts. That would just like that would fry the earth. Actually, no, I don't think that would fry the earth, but I mean that would definitely fry chicken.
That's awesome.
All right. Anyway, fried chicken. All right. Moving on. I think that once you get this, like, this will be like, oh, I get this. I can kind of hang with these. These problems aren't going to be that bad. And yes, I haven't assigned you guys to your homework yet. I'm going to do that. I promise. I'm doing that today.
Like building stuff?
Yeah.
When does this come in handy? I'm just wondering, you know.
When we're talking about
why.
when we're talking about capacitance and that kind of stuff, when we're actually talking about, because I'm going to introduce you guys about the capacitors and whatnot. And actually knowing about voltage kind of makes a big deal when you're working with electricity. Right? So that's kind of why I'm teaching about this stuff. All right, check this out. Do you guys remember adding? All right, so what I'm gonna say is, superposition. And I know that I know exactly what this is. Superposition of electric potential. All right, now you remember superposition of forces, right?
Doesn't depend.
That would be adding the forces together. Well, pretty much everything, not everything, but a lot of things can have superposition. And what is superposition? All it means is they can be added together. But guess what? Here's the thing that I think that you guys would be really excited about. Do you guys remember superposition of forces? Kalana and Deja, what did you think about that? Since vectors were a new thing for you. Was it hard? Was it easy? It was tedious. All right. It's because forces are vectors. But electric potential is not a vector. Electric potential is just a number. So when I add the electric potentials, all I care about are the numbers. So in the superposition of electric potentials, I don't need to break those things up into their components. There is no vectors associated with them.
Because we're talking about the energy.
We're just
not
talking about
forces.
the energy. And when we're talking about the energy, that is
Radius
not a
small
vector,
points.
it's just a number. It's just a
So
value.
Zero, I guess.
So when we're talking about adding things up, literally, you just add these things up. Like it's that straightforward. Yeah, I know. So once I explain that to you, you're like, oh, wait a second, I'm going to hang with this one. So here's that, ready? If I have a charge, and I put this charge at, the charge is Q equals 4.11 times 10 to the negative 9 coulombs. It's a small charge. Got it? And I put a second charge that is exactly 1 meter away. And that is, the second charge is actually 2 times the first charge. And it's negative. So it's twice as big and it's negative. Okay? What's nice about this is, here's my question for you is, what potential would I feel halfway in between? So 0.5 away and 0.5 away. That's all I'm asking. So, what potential would you feel from this charge over here? From this first charge, Q1. The potential you would feel is KQ1 over 0.5. That's it, right?
The other one is K.
And then this would be, the potential you would feel is KQ2, which is actually negative 2Q1 over 0.5. And then you just add them up.
So
So the potential you would feel between here is KQ over 0.5 minus 2 KQ over 0.5, which is actually just negative KQ over 0.5, which is, we calculated that to be, I don't really have the numbers on me, but it is, they didn't do it, or they did. Negative 73.9 volts. Yeah, this isn't bad at all. You want to see something that is hard? Alright, I'll show you. Ready? Here's the second. Does that make sense to you, Deja and Kalana? And Tiger? And Victor?
Yeah.
Like, you don't need to. I love doing this stuff because you don't need to, like, break it up into its components. You just add them. Alright, here's another question, right? Like, if I put a positive test charge over here, apparently the voltage over here is negative 73. Right? So it's actually small, and it's going to be smaller over here at negative 2. Yeah, it's going to be super small over there. And so this test charge will want to do what? It's positive over here. It's negative 2 over here. It's negative twice that. It's going to want to zoom that way, right? Now, there's one point in here where the potential is actually 0. where the potential that this thing feels total is going to be 0. Doesn't mean it's going to freeze at that point. It's just going to be like it's 0. How do you figure out that point? Where in between these two charges is this thing going to have a 0 potential? So all you do is this. Your potential is equal to the one felt from here. So that would be KQ over, I'm going to call it X, because I don't know what it is. It's not 0.5, it's X. It's somewhere in between here. We cool? And then I'm going to call this guy minus 2KQ over, what's the distance between here and here? 1 minus X. You got
So
it?
for this one, then
So
the distance for the distance we're talking for the second charge is relative to
well, yeah. I mean, what I'm suggesting here is that if you have one point over here and you have a second point over here, then the first column I said, okay, it's fixed distance. It's exactly halfway. What is the total potential? Exactly halfway between. But for this one, I'm saying, what if you're setting a distance x away? And I don't know what x is because I want to solve for it. Well, this is x, and this is right here is 1 minus x, if the distance between here and here is 1. You get it? All right. And then I ask you, when does the voltage equal 0? Okay, well, you just set that equal to 0. All right? Then solve it. That's all you do. Figure out what x is. Okay, fine. KQ over x equals 2KQ over x minus, or 1 minus x. You understand what I did? No, I just put the whole thing on one side.
Yeah.
Before I multiply, why don't I cancel out the k's and I cancel out the q's?
Oh wow.
Now I'm going to cross multiply.
Basically 2x.
So I have 1 minus x equals 2x. And I'm going to have 1 equals 3x. And so x equals 1/3. 0.333. And apparently if I'm standing at that point, I would have a potential of 0. The potential for me would be 0.
You understand that?
Sure, you just take something, divide it into 3 pieces, and stand over there.
Exactly.
So how come I'm just wondering why potential would be 0 and is there like only one left first charge?
What do you mean?
Once it leaves that the first charge area, the point charge.
Yeah.
Why isn't it just be 0 again?
Okay, well, here's what I'm saying. Here's what I'm saying. It's like, all right, so if you're over here and you have a positive charge over here, and you're over here and you have a negative 2Q. You have a positive Q and a negative 2Q, right? If I were to graph this, the potential for this guy would kind of go towards him and it would spike up over here. He would spike. Got it? The potential for this guy would spike down. Right?
It would spike out sooner.
Exactly, but he would spike down a little bit sooner because he would have a bigger inverted volcano. And where it meets in the middle is right there. It wouldn't be right in the center. It would be right in the center if this weren't negative 2Q. It would be right, but it's not negative. It's negative 2Q, so the volcano's a little bit bigger. In fact, believe it or not, I didn't realize it. I wasn't foreseeing this, but think about this. This will blow your mind. Essentially, Deja and Kalenda, this is exactly the problem I solved for you when I was solving your Algebra 2 math problem. Is right before you came, I asked Deja and Kalenda, I said, how are you doing in math? They said, I'm having trouble with this concept of intervals and whatnot. And I solved the problem for them, and I realized that, oh crap, this is exactly the problem. We can figure out exactly where the 0 is, and then we can use a test number, and we can figure out, hey, it's positive over here, it's negative over here. We figured out what the graph looks like. I know the graph. This isn't. Oh, fine. This isn't exactly the same problem, but it's. But if you wanted to figure out what the graph looks like, you would use the same exact techniques as what I just showed you. Oh my gosh, I didn't even realize that those were going to be related when I started off this lecture. I think that's pretty awesome. I will give you homework. I will give you practice stuff.
I mean, I can do all this.
Yeah, you can do
when
this
sitting
in.
here, but
I can
to
do this when
remember it, I
I'm
need to.
looking at you and nodding my head and saying yes, I understand. And then when you hit the problem, you're like, oh my gosh, this is crazy.
I have the same.
That's why.
All right, fine. I'll tell you what.
Worksheet, you have like 10 questions. You just do it.
Today I will go in and make sure I assign you appropriate homework for what you need to be doing. And I'm going to assign homework, okay? But I'm going to make it reasonable amount of time that's due, all right? I'm not going to tell you it's going to be due tomorrow or something like that. I want to give you homework so that I can basically give you practice with this.
I like the ones that you do in class. These are like these are super teaching, but some of the homework ones are like.
I will make sure that the homework I assign is is drawing on the same concepts as what I've been teaching in class.
Because I have some of the homework, I'm just waiting for the Dropboxes.
Yeah, I know. For this class, I've been sucking at Dropboxes and assigning homework. I'm sorry. But guess what? I learned what I'm going to teach you in STEM class. I spend all night learning what I'm going to teach you in STEM. So anyway, this is what my life is for now. Is these are brand new classes, so we're pulling these out. And plus they had me switch up, but I'm not asking you guys to go wah being poured this all day. But what I'm just letting you know, this is kind of I'm doing my best. I feel like I'm not doing that bad of a job teaching the class. I'm kind of doing a bad job organizing the class.
Oh yeah.
So that's something that I'm going to work on. I promise. But these are my smaller classes, so they kind of sometimes fall the wayside. But that's not what it's supposed to be. Actually, these should be my priority classes because they want to convert me into a full-on STEM teacher, and we haven't figured out what STEM is exactly.
So, if we're still doing physics, would this energy and would electron like energy?
No. If I taught you a full year of physics or even a full 2 years of physics, which would I think would be ideal, I would spend the first half of a year teaching mechanics, which is what I taught. I would teach the second half of the year probably doing thermodynamics, heat transfer, and then I would spend the another half of the year teaching electricity, and then I would spend the last bit teaching quantum mechanics. Which, if I taught you quantum mechanics, you would be like, "Oh my goodness!"
Doesn't it deal with atoms in itself?
Yeah, we're talking about we're not talking about atoms in itself. We're talking about like actual electrons, like just individual electrons.
The entire concept of things can be two
Yeah,
pieces at once.
but I mean, even in this electricity class, we're talking about actual electrons.
Yeah.
We're talking about moving electrons. Now, eventually, we're going to have a bunch of these moving electrons, and guess what that makes? That's electricity. Electricity is just a bunch of electrons moving across a conductor. So we're going to get there, we promise.
You know what I really wish we went over?
But I feel like we're doing a good job because we're doing like rigorous stuff. All right, anyway, I'll stop the archive. I'm done with class.